Good morning, everyone, and welcome to today's webinar, How to Maximise the Value of Your MET Testwork Program. This webinar has been presented by Dr. Leon Lawrenson of Mintrex. My name is Aidan Montague, and I also work for Mintrex, and I'll be your moderator for today's webinar. I'll hand over to Leon shortly, but first, just a little housekeeping so that everything runs smoothly. Main presentation will last about 25-30 minutes. And then we'll have about 10 minutes or perhaps more Q&A at the end. So the entire webinar is expected to last around 40 minutes, depending on the number of questions we get. Of course, you'll get an opportunity to ask questions during the webinar, but these will be answered at the end. You should see a question pane on the right of your screen. So just type your questions in there as the webinar proceeds, because during the webinar, you will be muted. So before we get started, I'd just like to introduce Dr. Leon Lawrenson. Leon has more than 38 years in-depth experience in mineral processing, particularly in the metallurgical mineral processing, design and engineering and consulting areas. He's also been a researcher and is widely publicized in both chemical engineering and metallurgical engineering literature. He was recently recognized as one of the top 2% of science and engineering professionals in his field. So now I'll hand over to Leon.
Good morning, everybody. I just want to make sure that I've got a bit of a trying to see if I can move this away. Just want to show my screen. Just want to make sure that the screen. So can you all see that? I hope that you can see that. Yeah.
You're all good,
Leon. Thanks. Today I'm going to have a chat to you about how to maximize value of your metallurgical testwork program, and it's basically a systematic approach on how to improve. So I'm going to use a bit of my experience over the years to do that. I've just got a bit of a delay on this presentation, so I just want to try to get it to the next slide. So unfortunately, let's do that. Okay, I'm going to use some of my experience to actually just share with you. And I want to just start off by saying there's no right or wrong answers always in life. There's just some guidelines. So I'll talk about a bit of introduction. I'll give you a bit of a project timeline and some stages of the project and what should be done, what should be evaluated, and then give you a bit of a rundown on what our flow sheet should be developed after you've gone through those various stages. What is the purpose of extractive metallurgy? And I think that is something a lot of people, battle with. But, why do we wish to perform mineral processing and even metallurgical techniques on ores? And you have to understand that the answer should be to do the absolute minimum to the ore coming out of a mine to turn it into a saleable mineral, getting the maximum net value. So do minimum to get the maximum. The more you do, the more it will cost you. And that is where the challenge comes in. So it requires an understanding of the process requirements to provide the customer with what they want. So at the end of the day, you want to walk through those various steps, but that should be a very important aspect of thinking. I don't want to do too much to get that maximum MPV, and that is a very important part. So I mean, just to give you a bit of an idea is, if you take alumina or you can have minimum effort. You can basically sold directly. Ores, iron ore is a good example. Coal, you don't do a lot to it to actually get it sold. A medium effort is probably a concentrate. To be honest with you, you want to produce a concentrate. You want to sell that concentrate, so you clean it a bit. You take some deleterious elements out of it, and actually you add some value to that. And then the maximum effort is you might want to sell a metal or refined intermediate. For example, you might sell alumina, or you might at the end of it sell a gold bar, etc. So that's your maximum effort. So at the end of the day, you're not going to do all the test work and everything to get, if you only need a minimum effort. Then you do the applicable test work. When you get to the maximum effort, you have to go through the whole range of test work programs and things you want to do. So if we look at a project timeline, just give you a good example. And it's something I borrowed with permission from SGS years ago, and then and I've adapted it a bit. But you could see that project will run through various stages, from exploration, scoping, pre-feasibility, feasibility to production. In that little egg in the middle, or you will see that there's most of your metallurgical test work will be focused on when you're actually starting with roughly scoping, pre-feasibility, feasibility. You will link your metallurgy to geology, you will populate resource models, and then you'll start with optimizing your NPV model. And in the early stages with exploration, you do spatial domain definition and then mineral processing, sample selection just before scope. So it gives you a good idea about timeline moving from left to right. And if you start too late with test work, you actually move this eclipse on roughly egg shape to the right. And if you go closer to production doing still test work, you actually really go into a danger area. And that is a very important aspect to remember. You should start early and you should do the right thing early. So what's early exploration? During early exploration, usually geologists is mostly involved. They will do a bit of lithology, which is a general physical characteristics of the ore. You'll do a bit of assaying. A very limited amount of mineralogy is done ever, except nowadays you get some of these more senior, bigger mining companies that might do a bit of mineralogy, especially if they go into a new ore resource. And then basically during early exploration, some people might even look at order of magnitude cost, but it's guess estimates. It's not really. So generally no real metallurgical data is available at this stage. The only information available is roughly the lithologies and where the ore is, where the valuable mineral, metal or mineral will be with regards to the other minerals in that ore or in that ore body. During the scoping study, you actually want to define it a bit better. So you actually want to find out roughly, okay, what I think the process will look like and what type of mineralogy is involved, so I can actually understand the process that I need to follow to actually retrieve the valuable metal or mineral in that ore body. So you're looking at mineralogy during scoping study. You might do some bench scale test work during that study. You might do factored recoveries or factored cost estimates if you want to do. But the data from a bench scale test work provides inputs to a preliminary process design and process specification. So that's basically that stage of the process. If you go to pre-feasibility, you want to do flow sheet selection, detailed test work, continuous process test work, simulations, major equipment costing, reagent consumption, energy, operating costs, all at an accuracy of plus or minus 25%. So you do need detailed metallurgical data necessary to do this stage. Now, one of the things that a lot of people go wrong is they actually start a pre-feasibility study and then do the test work, and they want to run the engineering continuous with the met test work. That's not the case. You need the test work results to actually, at the end of the day, make certain selection. If you are still not sure about your flow sheet selection, you might run parallel. But you have to understand that at the end of a pre-feasibility study, you probably very much would like to link and lock in your flow sheet, which you selected, and the test work should confirm that flow sheet to a great extent. So the earlier you start, the better, and that's a very important part of it. During feasibility, you get detailed flow sheets, equipment specifications. You could pilot or demonstration plant if you want. You do the capital costs and operating costs, and you base that on manpower requirement, reagent consumption. By that time, you've done the test work, reagent consumption is there, your power requirements is there, royalties there, you know what power is needed to grind the ore to a certain particle size. You've got all those things. The PDC is semi-fixed now, and you actually really know where you want to go with this whole process. And that will move into your process design criteria, which you will go into detailed design. So it include in that is your throughput, your feed grade, your unit process required for a flow sheet, the operating details such as residence time, reagent required, temperature, pressures, vessel sizes, power requirements, all those things is fixed into your process design criteria so that you can go into a detailed design and into your P&IDs, etc. So during detailed design and construction, you will review and monitor the designs, and you change changes are very expensive in this stage. So if you've done a DFS, which is at 10 to 15% accuracy level, you actually don't really want to change a lot of things during detailed design. That will cost you. So you should not do more test work. It should have been done by now. If you want to do something in detailed design and change it, it might be due to the fact that you might have maybe bought a second-hand mill, which is not exactly the same size that we had in a DFS study. You can adapt to that, but it's still a mill that produces the same energy or have the same energy requirements, and a mill that can produce the same grind size as you want. But changes are expensive. Commissioning is called an hot commissioning. You try to achieve the design specification, you sign off, and then production, where ownership retains and closure end of the mine life. So those are the steps. So what is a value proposition? So to try to explain to you a bit, but during greenfields or brownfields, even brownfields operation, the test data gets used into a box which we call analysis, audit, and modeling. So you take that test data, you analyze it, you check it, audit it, check it if it's accurate, etc. Then you model and simulate things. So out of that comes optimized process parameters, and you can use that into studies. If you, for example, have an established operation with the brownfields, and you actually do have some plant data, and you're looking at a new exploration area or a new resource, which might be different or very similar, plant data can be used because you've got a lot of years of experience, 5 or 6 years. You can use that information as well, and you can actually try to use that information, and it can actually go from plant data right through to the scoping level, or you can actually use it in process optimization and reconciliation. So it's all of that is valuable information. So the process, and I'll talk to you through a bit of a process now, is actually experimental design. So effective test work design, and then ensuring the test work results reflect the actually achievable results. So the representativity and variability of your test work, and we'll chat about that now, the geometallurgical modeling, so the mineral variability modeling within the ore body, and then your analysis of your test work data. When you have an established operation, you'll do the data mining, you still do geometallurgical modeling, you might do process optimization and reconciliation, and some of that information can be used for a brownfield. So they're applicable to both. So let's look at a type of hypothetical typical gold flow sheet. Now, during a scoping study, or at an early part of a scoping study, when maybe guys have done a few bottle roll tests just to find out if, and I'm just using gold now, say gold is leachable and yeah, it's free milling or not free milling or etc., etc. You will have a hypothetical gold flow sheet in your head. And that flow sheet should be looking at, okay, I need to get this material to a certain particle size. We don't know yet what will be the optimal particle size, but I have to get it down to at least some particle size. I actually then have to maybe take out some gravity if it's needed. If there's gravity component, I actually then probably have to go and leach it, doing CA adsorption tests, etc., etc. All these is possible things that you have to test during a program. If the flow sheet is simple, it's fine. If the flow sheet's complex, it becomes more difficult. But at the end of the day, when you start in the scoping, you don't really know if you need all this. So you have to manage what is needed and how can I make certain calls. So there's a few basic things that you have to follow to make sure that you do that. And I'll talk to that in the next few slides. So what's the factors impacting a process test work requirements? Now, the first thing that you have to understand is the complexity of your ore body. If it's complex, if it's difficult, if it's for example a mineral or metal or gold, so say gold or whatever base metal, which is really enclosed in other minerals or locked or associated with some deleterious minerals, it tells you a lot about the complexity of the ore body. So the lithology, mineralogy, it's an important part to look at. Then is there impurities? Is there things like, yeah, there's gold, or there's maybe a base metal copper, but it's with it's also associated with some maybe arsenic material, etc., etc. Are these going to influence your quality of your concentrate that you produce? What is the impurities? Are they problematic or not problematic. So the amount and chemistry of the gangue, what you need to be removed, have to be understand, and the variability of that ore body. Is it homogeneous or is it very different? Now that's where the processing people have to talk very in detail with the geology guys and understand the complexity of the ore body. It's basically a sit down, go for it, understand it, that they explain it to you, and so you can ask the right questions and try to get the right answers so that you can understand that complexity of the ore body. Now, to be honest with you, nowadays we're actually slowly moving into more complex ore bodies. So basically what's happening is, you know, these easy free milling ore bodies, they're not behind every stone anymore. You actually have to really battle to find them. And if you find them, you usually find them in areas where there's a scarcity of water or there's a scarcity of something else. So there's always a complexity with it. But some of the ore bodies that's not been treated over the years because it just looked too complex is ore bodies with a real complexity. And those are the ore bodies that we now slowly looking at and slowly start exploring. And it means that the standard type of test work that you've always done is not always 100% applicable to this, and you have to think a bit outside the box. And that's where the teamwork with geologists and mineralogists and processing guys, it becomes very important. And then you have to look at the grade of a target minerals or metal that you actually would like to achieve. So what factors impact the requirements? Another few is your geometallurgy. So we know that during the early stages of geology, there's quite a bit of geochemistry information available. And I remember when in the early stages in the 80s and 90s when I worked at research labs in Engelbergen, for example, that, you know, we knew and we understand roughly the lithology. We had a bit of assaying, etc. And what we've done is we slowly tried to link some of that geochemistry to the mineralogy. And if you can find a link, you're actually very good, because that will help a lot in the modeling going forward with the resource and reserve. If you can't find it, you should try to look at it, or you should try to link some of that geochemistry and mineralogy to metallurgical data. So, you know, if you have a good geochemistry, can you link it to some of the mineralogy you understand and model it? Can you link some of that geochemistry and mineralogy to the metallurgical data that you have? Can you model it? And then can you link it to some physical properties? So using mapping and analysis is an integral part of that step for geometallurgy. So you can understand the ore body and you can actually give some relationships back to the resource guys so that they can model it and then actually move some of that into a reserve by actually adding some economic values to it, so it can go and be modeled into a reserve as well. So what is other factors? The size of the ore body. Large ore bodies may allow process options due to economics of scale. You know, one of the things I want to mention a lot is if your ore body is still only a 3-year resource, is, you know, and you only have a small plant that you're actually going to design, don't you need to do a bit more resource work and maybe a bit more metallurgical test work before you try to understand what flow sheet will work there? We found that sometimes guys will do a small ore body and then suddenly the pit becomes 3 times the size and the total mineralogy changes and it's not a homogeneous ore body. And what you thought will be the flow sheet initially is totally not a flow sheet. So you're going to repeat work if you don't think about it. So think about things like that early in the project. What's the estimated size of the ore body? And what's the assumed final product? That's a very important part of that. There's a massive difference between a concentrated intermediate product, metal product in costs and effort to actually get to that stages. And good examples is, for example, if you want to produce some final products, you know, which actually increase the complexity with regards to the processing, you know, your costs just go up exponentially, and you have to understand, is it worth it, or am I going to sell a concentrate and not getting into that final metal product, so that you don't do all that test work and spend millions of dollars at the end of the day, and then only say, okay, now I'm going to build a concentrate plant, but you spend all that other information which might not be valuable at that stage. So think about what you want to deliver. So as soon as you got that picture, so you got a rough, you understand the lithology, you roughly understand something about the mineralogy, you had a discussion with your geometallurgist, you understand the association of the valuable mineral or metal within that mineralogy and geochemistry and lithology, and you roughly have a rough flow sheet discussing this is probably what will work. Then you will go and say, okay, I'm going to do some test work. Now, the level of the test work will depend on the level of the study, and I will say that a bit later in the presentation. But you're not going to do detailed comminution test work at scoping level, except if you feel that your, for example, just give you an example. If you're in a territory where energy is going to cost you a lot of money, and it's probably going to drive the project. And you also realize that through mineralogy and geology and the lithology, this looks like it's going to be a bit of a tough, hard ore body. Then comminution test work initially will, and more detailed and more variable test work will be very good, so that you actually don't underestimate the comminution circuit that you actually will have. So it's a thinking thing of how much is needed at each stage. And there's no answer about, you know, if somebody tells you need 5 samples for this stage or 50 samples for that stage, I tell you, you're wrong. You need to understand that you covered all aspects, that you actually covered all the spread, the grade, etc., etc., and I'll get to that. But the level will depend on what level of the study it is. So you will do comminution, you might do some flotation work if it's needed, you might do some physical separation test work, you might do some leaching test work. You might have some environmental issues that you have to look at, you know, and then you will test the mineralogy and geochemistry. And I'm adding the bottom 2 because sometimes I find even at early stages, effort goes into the comminution, flotation, and the first 4 just rough tests, but nobody actually looks at the mineralogy. They actually think they know the mineralogy and they don't really get that. And because it's expensive, but the more you do early on, the better you understand as you go along the process. So then we get into that. So you know roughly, okay, I've got a process. I know what I want to deliver, a concentrate or a final product, and I now also know roughly what I think we should be testing. Now, the next thing is, how do you select samples? You know, you have to go and test some samples, etc., etc. Again, it depends on the level. So sampling of grade or metallurgical properties underpins a successful mining operation. Okay, it's not grade only. Please just not. It's a combination of the 2. It's actually grade and metallurgical properties. If you only design for grade, you're going to have major problems. You only design for metallurgical properties, you're also going to have some problems. So you have to understand both. So poor plant performance will usually relate to a poor quality and number of samples being tested, poor or inadequate testing, or often both of them. And that is a very good example to have. Poor quality or numbers, and it's not only numbers, it's quality as well. Poor or inadequate testing, or often both. So from scoping to DFS, more samples and testing are required. So as you move along that chain of the studies, you need more samples, you need more testing, and you need more double checking and variability, etc. So DF require large-scale testing. So first-class test work, and these 2 bullet points I want to just emphasize very far. First-class test work on poor samples does not add value, and poor sampling equates to lost time, high cost, and project cost risk. So remember that. So sample selection, you can have composite samples, variability samples, or you can have bulk samples. I mean, those are usually the samples we're talking about when we do samples. Now, the interesting thing about this, composite samples, it's usually a sample bucked together with various intersections within a domain. But a lot of people do composite samples where they actually just mix domains. They mix lithologies. They just make a composite sample, 3 of them, and they actually make composites according to grade. Do not make composites only according to grade. Make composites according to your domains, your lithology, and your mineralogy with grade involved. Should samples present the ore types? Yes, it's very important. And during compositing, if you do composite, think about ore type and variability, the number of intersections and angles, the depth, the weighing and the composite of samples. And remember, composites smooth variability. You take out variability by making composites, especially if you're making composites over lithologies and over domains and over mineralogies. And just look at grade. So beware of average ore composites. It's very, very dangerous. So that's why if you do composites, and a lot of people do, bring all these things into consideration, and then remember when you do it at the PFS and the FSH, do variability samples, which is not composites, to actually see if your plant's not seeing those composites and it's getting certain areas or blocks being treated through that plant, can it handle it? If you don't tested that, you don't know. So variability samples is just that. It's individual samples, usually diamond drill core, or constrained composites that represent a specifically metallurgical response, right? Hard or soft, low or high recoveries, locked or unlocked, etc. It's used to assess variability, so assess plant design suitability for different types, and it do allow you for geometallurgical mapping and modeling, because some of that you can relate back to the mineralogy and lithology. It's important that a study provides data on initial plant feed. It is the first few years of operation, not just a medium to long-term feed. You have to understand what you're going to feed. So the mine schedule is very important. And if people give you a mine schedule with 3-4 metallurgical test work and don't bring into the metallurgical parameters into that, you're actually really designing plants for certain times where it's actually maybe very hard, and then other times it's not going to running at all, or maybe it's not going to be fully utilized. You know, you have to be careful. You have to understand what you're going to do. So if you've done, just give an example, if you've done composite samples and done all these grade variabilities, etc., and use to smooth something out and just making grades, and you're suddenly not running a ROM pad which you actually can feed the plant with that composite, you're actually feeding a plant with different material all the time. If you haven't done a variability testing or actually tested the variability within that whole open pit or underground, you actually have major problems, and that's a lot of times it happens, and that's what you have to look at. So bulk samples, that's big samples, 1 ton to 100,000 tons. It's usually when you have a pilot plant, when you actually really want to run a pilot plant to make sure that you actually can produce what you think you can produce, or a trial plant. Sometimes a trial plant is where you actually want to make a small plant, run it, and then just expand it and make it later a bigger plant. It's expensive. Care required for extraction, often relative costly and not always more representative. So you don't have to do bulk sampling, but if you want to do bulk sampling, for example, if you want to do for ore sorting, for example, you want to do it in a big scale. If you want to do HPGR, you want a bigger sample to do that. That's important. So you want to follow that. So you have to understand when you need it. So this is a bit of a graph, just quickly looking at sample selection, and that's there for your reference. But you can see for scoping, you'll do a bit of laboratory test work, PFS, laboratory test work, and maybe small pilot if it's needed, and DFS the same. You only will really do pilot tests or trial plant test work at DFS and early engineering design if it's important. Okay, and that's the type of samples that you need. So you diamond drill hole or large diameter or bulk samples, so you can see that. So ore preparation, what do you want to know there is how hard is the ore, what size it have to go to, how much particle size to reduce. So you have to do test work to understand the hardness, so you understand the energy. And you want to understand also what's the particle size that you have to go to actually extract the material. Then you go and see what equipment you needed, how do I model it, and how do I select and design those equipment. Flotation and leaching. Is it possible to upgrade the ore in some way by like gravity or flotation? If you can do that, how can you do it? Should I test it? What test work should be done so that I can design a gravity concentrator or a flotation circuit? What's the subsequent process? Is it leaching, smelting, pyrometallurgy, hydrometallurgy? Is there temperature or pressure involved in that? Should I test for that? And then what is the process control parameters that I have to look at? How can I model that equipment and how can I design it? So the test work gives you the PDC, and that helps you to actually define the model and the equipment and the selection of the equipment. And then separation processes, if you look at solvent extraction, selective precipitation, leaching, or selective leaching, precipitation, crystallization, same thing. What is the principles? What's the techniques? And what type of things do I need to test to make sure that I understand it? So each one of those unit operations that I just mentioned, at the end of the day, they provide you with information so that you can put a PDC together. And that PDC will size equipment, will make sure that it will explain how that process plant should operate, and that you can use to actually size and design a flow sheet. So then you move into your mass and energy balances. You use your spreadsheet and use process modeling software to do a mass energy balance. You look at the energy requirements to actually do that, and what energy source is going to be used, electricity versus diesel or gas or natural energy nowadays. I mean, energy such as solar power, etc. Your water balance, is there enough fresh water or not? If it's not fresh water, is there enough other water? If it's saline water, what do I need to do? And while I'm in that, also remember that you have to do your test work within the type of water that you usually would like to use. And then I haven't mentioned that, but that's very important. It's important. If you've got saline water at 190 TDS, 1,000, for example, and you do test work in fresh water, you know, the two have to relate, and that's important. The other thing as well is you realize that you have 190,000 TDS water, you still need to get that water down to less than 10,000 to do, you know, work in your electrowinning and actually your elution circuit. So how are you going to get that water, you know? So you actually do need a small limit of fresh water. You can't bring it down to those levels with any of these osmosis or any other techniques. Limitation to discharge water, storage and evaporation, things like that. You know, you go to very dry areas, you want to use all the water. Are you going to have, for example, dry stacking, or you're going to have a TSF, etc., etc. So it's a thinking that go with that. How it impact your CAPEX and OPEX? Lastly, so complex ore bodies usually require more complex flow sheets. Complex flow sheets imply more equipment and better process control. More equipment and process control usually lead to higher capital cost requirements. More equipment and process control often leads to larger staff complements and obviously higher OPEX. So all of this, you add to it, you make it more complex and more costly. Grade impacts on the process option, which in turn impacts CAPEX and OPEX. So lower grade ores, you should look at, maybe consider other options, or you have to have a very high resource if you have lower grade ores. If you have an ore of 1 gram a ton, for example, gold, and you only have 3 years of mine life, you know, and you want to build a process plant with a CIL, etc., you think it's going to be worth it, the energy, etc. That's a question you should ask early on. Complex ore with significant impurities may require more complex flow sheets due to requirements for the selling the final product that you're going to sell. So you have to do a market analysis to understand what's a product that you can sell and what's the limitations and the fines on those products. And then oxide versus sulfide ores require different processing options that you have to understand and very carefully consider. And if there's a change from oxide to sulfide, etc., through the process mine life, you have to actually know that your process circuit have to adapt to that, and that you have to test for both. And that will impact your CAPEX OPEX. Just for example, free milling versus refractory ore, you can see the chemical treatment, you know, there's different things, and all these cost money. And if I look at the next slide, it's a good one. For example, a free milling circuit, you might have a primary and secondary crusher. Refractory circuit, same. So it's not going to be much different. You've got it there. Your milling, it might be a SAG or a ball mill, or both. Your other one, refractory circuit, might be same, both, but it might be a bigger, depends on the hardness of the ore. You might have a gravity circuit on the one, might have a gravity circuit on the other, and then you start looking at pressure oxidation, roasters, bioxidation, other techniques with refractory circuits, which is not in a free milling circuit, and neutralization, and then you get to CIL. So you have a few steps. If you go back, you can see you have quite a few steps there, from pressure oxidation to bioxidation to roaster to neutralization, which you might have to add, even fine grinding, which I didn't even add there, before you might actually get to other circuits. So there's a lot of differences in a free milling and a refractory circuit, which add to the complexity and the cost, and that have to be tested and make sure you actually want to put it into your flow sheet, and it actually gives you value. And sometimes just for concluding the result, sometimes, just before I get to this last slide, is it's important that you do understand that there's a difference between necessity and nice to have in a flow sheet. And what I'm trying to say here is that if you want to make sure that, okay, I can get 91% recovery if I mill to 125 because this material is incredibly hard, and I can get only 92.5% if I mill to 75. Do you really think that 1.5% is going to give you, is going to be better for you in the sense of a cost? If you do economic analysis, you probably will find that it's cheaper and it's more economical to run at 91% and at 125 than ever to run at 75 in there. And you have to do that analysis. It's not to say it's going to be there like that, but you have to do it. It's not ounces is king. It is how you produce those ounces, and if that is king then. So concluding comments, you should understand the mineralogy of the ore. You should understand the complexity of the ore body, and as soon, the earlier part you understand it, the better is guiding it forward. You should ensure that the test work is aimed to provide the data to make the level of study requirements and the level of appropriate flow sheet development. Okay? You should make sure oxides, sulfides are required very different processing options, just for example, or any, you need to test them differently. You understand that you actually, if you have both, you have to test how you want to go forward. You decide on your final product. What will be that final product? Sometimes it's not easy to decide that early on, and you might need it a bit later on. But then again, then you need to do some of that test work and spend the money to actually help make that decision. If you don't spend the money and you don't do the test work, it's even after you get your feasibility, you can't make that decision, you have a problem. Your process complexity and impacts on capital they have a major impact on capital and operating costs. So keep it as simple as possible always. So always try to make it simple, easy, and then add things if you can't do it simple and easy. And that's rather than start with a very difficult thing and then try to take things away at the end because it's too expensive. And that's it. And I think what I've tried to do today was to actually just provide you all guys with a bit of a feedback on or a thinking, or what type of thinking you should have if you start developing test work programs. And don't do it as a recipe and just do the same thing all the time. If you go to the labs, they're going to give you a recipe because they want to do certain things. Think about it. Think about the level. Think about selection. Where do you take the samples? And lastly, I want to leave you with that. You need to test the whole ore body, the whole resource or reserve. Actually, at the end of the day, the reserve. You have to actually understand the depth, the geographical location of the samples, the grade, the mineralogy, where it's taken, etc. And you have to show at the end of the day that you actually tested all those variabilities within your program. And again, I'm a very strong believer that it's not about 5,000 samples, which is very much a BHP system where they have the money and they can test a lot. It's fine, it's no problem. You can get away with 20 samples. You can get away with 10 samples. Depends on the complexity, depends on the homogeneity, and depends on if you can prove that you actually tested all the variability within that perceived resource and reserve that's going forward. Thank you very much.
For any more questions, please type them into the chat box on the side. One question, Leon, just a bit of clarification in regard to variability. Can you clarify how we ensure that the process flow sheet can handle variability?
If you, at the end of the day, that's what I said, you have to understand that if you have a flow sheet, maybe you should just mute yourself quickly. If you, at the end of the day, if you design a flow sheet, you have to understand that during that flow sheet, that plant will probably see any variability by itself at some stage through the life of mine, and you didn't blend the problem away. So if you haven't tested variability, so for example, if you say, okay, my average hardness of my ore is, let's give you an example, is this is going to be a Bornbull index of 21. So it's a hardish ore, it's going to have a problem. That's the average. But at some stages, you might end up at 27, or you might have 16 or 15 kilowatts per hour per ton. If you're going to mine for a few months at 27, you're not going to get the throughput. You're not going to get the recoveries. You're not going to produce the ounces you want to produce. So you have to understand that the variability have an impact on your design. And it's very much how you use that variability in your mine design and your process, not your mine design, your mine production, and then at the end of the day of your financial modeling. You can't design it out of the process flow sheet, unfortunately. You can only design for a certain throughput and a certain, but there will be, obviously, only any process flow sheet can handle quite a bit of variability within it. But yeah, if you design suddenly for a 27 and you design always for 27, you're going to have half the time at 21. You're going to spend quite a lot of capital initially, and you're never going to get the, drive that engine full time. It's like driving a car. If you're never going to, you have a 4-liter engine, you're only going to run at 40 k's an hour all the time, you have a problem.
Thanks, Leon. This next one, I think you've touched on most of it, but just to summarize, in your experience, what are some of the major traps you have seen in the met testing process?
Two things. One is probably composite samples. I'm not a big fan of composite samples, especially if it's done for grade. When people say I've tested low grade, medium grade, or high grade material, you take all the lithology, mineralogy, and other things away. So you're smoothing a lot of variability and don't test variability. So you're actually saying, yeah, I test for grade and things like that, but you never test it for other parameters which will influence the throughput and a few other things. So that's a big thing. Only making 3 big composites and testing and be happy. And not doing enough variability samples. Yeah, variability samples is where you're actually testing those outliers and things that we want to make sure. And then the last one is doing the wrong test work. I mean, it's obviously a, and that happens as well. Sometimes people will give you a test work flow sheet and say this is what to be done, and it's a very standard one, and there's a few of them around. But if it's not applicable and you spend the money, is it useful? Or is it not useful? For example, you might get people who say, oh, I'll get away with just bond and rod index and crushing index and not do SMC tests or AB values, etc., for sag milling, etc., because I don't think we'll have a sag mill. You still need all of that information to actually make an informed decision.
Thanks, Leon. I think that's all the questions, unless there are any more questions. I don't see any more questions in the chat box. So I think we will close the webinar, but before we do, thanks to everyone for attending. I hope you all enjoyed it, and thank you, Leon, for an excellent presentation, and look forward to having everyone on the next webinar. Thank you very much. Bye then.
Thank you. Bye. Thank you. Bye.